Good morning. We start our lecture, and we concentrate on the problem we had already discussed during the previous lectures. Um, First of all, I hope you hear me. And second, the recordings are in YouTube. If you find my name, if you try to find my name and the name of the course, you will find the lectures, the recordings of the lectures. Most of them work quite well. There is one which you lost something because there were problems in connection, but in general terms, it worked well. Okay, so as you may remember, our problem is that we try to understand whether replacing conventional plastics, therefore plastics obtained from oil, with bioplastics and or bio-based plastics is useful in terms of sustainability. As I have said already a number of times, there is no question about yes. This question is not yes or no. It's because it depends on where you are, on what are you going to produce with this kind of plastics. Because, for example, now we have the question of less plastics. Someone says also, you may know the movement which is around Greta Thunberg, which you may agree or disagree, but the question is not that one. The question is that when they talk about plastics, they talk about some specific problems, which are, for example, the fact that you have a lot of plastics into the sea in form of fragments, the so-called microplastics. Microplastics comes from the sea as well as from the land. There is also a lot of plastics which is thrown away on sea. For example, fishing nets, which are in nylon, which are in polyamide, are a good example of that. Apart from that, you find out that there is an excess of production of waste in terms of plastics, especially, and some of it is dispersed into the environment. The question which is posed is therefore twofold. We have a question about the substitution of plastics, the conventional plastics, with other products based on bio raw materials. In other cases, there is also the question of, the two questions are connected in reality, the questions of using waste. And in the last lectures before Easter, after Easter, you will have Professor Cristofanelli, which will talk a lot about for a couple of weeks about energy production and the questions about how producing energy from oil and other sources, what is happening in the conventional ways of producing energy. Because as we cannot get rid, we need to be honest, as we cannot get rid of plastics, of conventional plastics, we cannot get rid of conventional ways of producing energy. For example, oil, natural gas, and so on. Even coal is still in the picture and will stay in the picture, especially in a number of countries which have the possibility of getting coal at quite reasonable price. So we need to be honest about this, and we need to be try to be balanced about the fact that we want to pollute less and the fact that we are still using a lot of fossil combustibles, fuels, and also plastics. Okay, so a question that was raised already last time is about biodegradation. Biodegradation is a sub system of the whole degradation. Degradation may happen for a number of reasons. You may degrade plastics. You may degrade plastics because of, for example, the action of light and sun. For example, you may have a, in that sense, you may have a photo degradation. Or you may have a degradation due to mechanical actions. You may grind the plastics, or you may let it decompose for as mechanical effects of just stresses and so on. The problem is that there isn't much mechanical degradation of plastics as such, of petroplastics, during at end of life. In other words, please remember that if we want to recycle anything, we need first of all to grind, to chop it in small pieces, and in the end, this can allow also other forms of recycling, so thermal recycling and chemical recycling. Okay, so we suppose that we are able to degrade plastics. We are able to degrade bioplastics, but there is also a little bit of possibility of degrading petroplastics. It is not true that petroplastics are completely not degradable. Well, they are not degradable during service, but they may be degraded because of the effect of some bacteria. Which in general terms may attack the surface and the plastics and then proceed into producing some polymers. You can come back even to the monomer, and of course it will the process of decomposition leads to carbon dioxide, water, and other products. In the case of petroplastics decomposed by bacteria, you may find only carbon dioxide, which contributes to greenhouse gases, which contributes therefore to global warming. And of course, the process starts from the surface, and then there are enzymes which are able to attack the polymer chains. There is a lot of discussion about enzymes attacking also petroplastics. Why so? Because, let's step back a bit. The main bioplastics which is used also in Europe at the moment is polylactic acid. Polylactic acid is not a new idea. Polylactic acid can be developed from corn starch, from glucose, and then glucose or sucrose, which is a dimer of glucose. Anyway, from sugars. And you get that polysaccharide starch. In the end, you get to plastics because you plasticize starch with some plasticizers like glycerol, etc. We need to be clear about that. There is an American way of doing things, which in America they have, in the States, they have discovered. Well, this was not a new thing, but because also already Pasteur in the 19th century, Pasteur has done a number of chemical work, which is still actual at the moment. He found out that it was possible to extract a polysaccharide from just by fermentation, and this led to a number of works on trying working these plastics from polysaccharides, which came out into doing this production on polylactic acid, this patenting of polylactic acid, which was already done by DuPont at the end of the 20s. DuPont is a big name in terms of plastic because they hold the patent for polyamides, for nylon, which has been the most successful plastics in the post-war for competition with steel. For example, you are able to make ropes that you are able to make even structures like springs with nylon, which wasn't the case for all the rest of plastics. And having said that, polylactic acid hasn't been a huge success in the States, although although it has been around for around 90 years. So in practice, what the American way of doing things involves trying the biodegradation of plastics, having conventional plastics and see if we are able to biodegrade them. You were seeing last time that we were talking about polystyrene, especially the foam form of polystyrene, which we know as foam, and which is used a lot for packaging, which you are able to decompose by effect of bacteria, which then are able to mineralize their fecula, so their excrements are mineralized. When we say mineralized, we mean that everything has become inorganic. Okay. Following our exposition, we find out that we want to understand whether we can, so the approach can be different, but lead to the same question: whether biodegradable material can be good for the soil. I can fragment them. Biodegradation starts from biodeterioration. Biodeterioration means that the surface is attacked by bacteria, which are able to fragment the plastic. They attack the plastic from the surface. Please remember that plastic and polymer are not synonyms. The polymer is the main part of plastics that allow plastics to work as a material. We define a material something that is able to withstand a force. The material needs to be able to withstand a force of any nature. It can be a tensile, compressive force anyway. Depends on the kind of object you create, but materials are able to withstand a force. So the polymer in itself is just a molecule which is not able to, with which you are not able to produce any material. Instead, if you put together plasticizers and you can put together some ceramics and some other additives, you create plastics, and plastics is a material. So from biodeterioration, there is an attack of the surface, then it leads to some modification. Polymer is modified, then it's depolymerized, in the sense that in general terms we can say that a polymer is stronger as far as it is longer and terms of polymer chain. If the polymer chain is longer, then the plastic is stronger after the introduction of the other elements. As I was saying, plasticizers, ceramics, rheology controllers. Rheology is that part of science that studies how plastics, in particular, well, all fluids, but plastics in particular, flow when they're put in a mold. If the rheology allows it, we are able to mold, so to produce something. Okay, and then you start depolymerizing. So depolymerizing means that the chain becomes shorter and shorter, and in fact, the mechanical resistance as well becomes lower, and it fragments, it decomposes, etc. Then there are some hydrolytic molecules, in the sense that you are able to, there are other molecules which are introduced, and they are able to make some parts of the material soluble water. In the end, you come out with assimilation, into the soil. In practice, you are able to be assimilated into the soil, introducing some effect. What I am saying by that, you may remember the fact that, coming back to Greta's problem, if you put microplastics in the soil and they don't have any action on the soil, they become just a problem. Also because they are not inert, because if they were inert like sand or clay for the soil, they adapt to soil as such. Instead, if we have plastics produced from the petrol, which is in fragment not too small, when Greta was talking about microplastics, she means plastics fragment of dimension in centimeters or a few millimeters, which can be ingested by fish, which is one aspect, but which can also be burned for some reasons. They may develop volatile organic compound, the so-called VOCs. In the end, assimilation means that they are able to be in soil, producing some action. So feeding some microbes, some bacteria. They are able to provide proteins and lipids, which is characteristics, of course, of bioplastics. But for some reasons, it is not completely true to say that even petroplastics can not be degraded, because in the end, even hydrocarbons have the disadvantage of not having, as you know, oxygen atoms. The fact that the hydrocarbons, I mean like alkanes, olefins, and so on, they don't have oxygen atoms, and therefore they are not able to be soluble in water and so on. They are not water soluble. In reality, for plastics, this may happen as well. This may happen because in reality, in most cases, plastics are produced by excluding polypropylene and polyethylene. They are produced by molecules which have some oxygen atoms, because they might be used as plasticizers and so on. There is always a part from which they can be attacked. In any case, they can provide we can provide some. There is also the case that there are some bacteria which feed on hydrocarbons. So even this is not completely true. Since we are at the university, we need to be less, I would say, naive than Greta. Although it's a person I personally like, but we need to be less naive and to say that there are other ways. There are also ways. There is a lot of research into that. I would be happy to provide you some references. I have given you some into the lectures, but anyway, there is a lot of research on how bacteria can feed on carbon produced plastics. Anyway, what we need is that in the soil they provide some nutrients for microbes, for bacteria, and therefore these are able to create a community and to pass their life to other decomposers, and developing some enzymes, and in the end they are able to create other. You have this strange cycle. You see at the top, strange in the sense that it's a bit cumbersome because you don't expect that. These microbes may develop some enzymes which are able in the end to reproduce biodegradable materials. Because there is this fact that bacteria are even able to develop some plastics. There are bacterial polymers which might be built with additives into creating plastic. And therefore, you may complete the cycle. So, biodeterioration is just the beginning. To conclude on this slide, biodeterioration is just the beginning of all the process that leads the assimilation into soil and then to the production of other biodegradable materials. Okay, this says about the same things, but it's now the time, since we are interested in practicing of what happens, to have some more information after we have ensured that there is a biodegradation, then a biodegradation, then it goes into fragment and it can be assimilated. What is not written in this slide with respect to the previous one is that after you are assimilating the soil as microbes can even be retaken from the soil, taken away from the soil, and reproduce other plastics. But apart from that, it is important to try to understand how it's possible to measure if this works or not. This might be not always obvious because there are some measurements which are quite fuzzy because, for example, measuring gases is not always the easiest thing to do. We measure biodegradation by the evolution of gas to see that it starts producing some gas, then it starts degrading, then you find out that in biodegradation gases are produced more. There is a lag phase, which is an initial phase where there is a non-uniform production of gas, because of course it starts some biodeterioration and then the material tends to be decomposed gradually. Then there is a really biodegradation. After that, there is a plateau phase. Plateau phase means that until everything stops because the material has been completely decomposed and assimilated if it was put in soil, of course, mashed. We try to help. We try to help starting from a fragmentation, mechanical fragmentation. But please consider also that we have no instruments and it would be too expensive to decompose plastic to well, mechanical destroy plastics. Probably decomposing is not the right word. Mechanic, it applies to biological organisms. But if we mash that plastics in mechanically, we can mash it into millimeters fragments, not into micron pieces. So we help the biodegradation to be set. Of course, there are physical methods because you lose mechanical strength, mechanical properties, strength, stiffness, hardness, etc. You might change color as an effect of that. You might have a change of color, which is obvious in biological phenomena. Change of color is an obvious indication. So you have a visual inspection. It's like the fact that we see mold on our food by looking at it or doing any analysis. And of course, with food we have also the indication. But before that, there is a visual inspection. And we have, of course, mass loss. We need to weigh the plastic and see how mass has been created. We have already said that with respect to composting. Composting means that we would like the material to have a work in terms of action on soil. Composting, I would say, it's more than just assimilation. You can assimilate, but not be yet composted. You may assimilate into soil, but your action might not be sufficient. Might be sufficient to feed bacteria and microbes, but not sufficient to create a compost which would be effective for the production of crops, etc. In other words, in simpler words, you may feed bacteria, but for example, you may not be able, the biological action might be low level to, for example, being able to crop, crop. For example, you want to plant potatoes. Your potato might not benefit, your potato plant might not benefit by your soil with added fragments of assimilated bioplastics. Of course, there are measurements of mineralization. We want to be clear about the transformation of waste into inorganic matter. Most of it we would like to transform into inorganic matter. Some would stay as feeding the soil, but the other option is to transform it into inorganic matter. As we were saying before, styrofoam, for example, we transform it into inorganic matter, which means that it's not compostable, of course, because it doesn't feed the soil, but on the other sense, is not harmful. It's also inorganic, so it doesn't harm the soil. It might also be possible It might also be possible that it mixes easily with inert and therefore is usable also in land filling. Land filling doesn't create a problem. And that investigation on mineralization of petrochemical plastics like pyrophore started from one consideration which is very, I would say, even cynical. But the consideration is that plastics is still dumped everywhere. So it's still even used for land filling. Pieces of plastic are still even used for land filling, for example, even to consolidate soil, which in principle wouldn't be terrible if it wasn't to develop volatile organic compounds and if it didn't dissolve into the soil substances that, for example, chlorine-based or chlorine or fluorine-based substances that would harm the microorganisms and also the larger organisms which and which are important, for example, worms and so on, which are important also for the management of soil. The importance of earthworms, for example, for soil is essential. If you give earthworms substances full of chlorine and fluorine, it's become also because many of these substances are, I would say, all of them are either acid or alkalines, and therefore they change the pH of the soil, which ultimately harms also your possible production of crops, etc. Having permitted all that, mineralization is calculated by the amount of carbon dioxide produced. You may remember that from your chemistry knowledge that carbon has got 12 of atomic weight, atomic mass, and then you have 16 for oxygen. Therefore, the molecular weight of carbon dioxide is 44. It's not surprised that if you want to measure and trap carbon dioxide, you detect it from carbon, and you have to make this proportion, the proportion between 44 and 12 to obtain carbon dioxide from carbon. Then you have the degree of mineralization, which is expressed by the carbon dioxide in the material from which you subtract the carbon dioxide from your controlled sample, a sample in which there is no carbon source, basically inorganic one, which might be a kind of ceramic also, like pure sand would be pure silica. Would be, for example, a control source. Then you need to inoculate something, because the mineralization is carried out by the work from some bacteria. You need to inoculate some bacteria in some amount, which is, of course, always is calculated by experience. Use like literature and so on. You inoculate the right amount, and then you measure the mineralization. The right amount, which depends on bacteria and so on. Because, of course, every bacteria has got a different possibility to mineralize. Then you measure the degree of mineralization. And you can measure also the assimilation. The assimilation means that you would like to know which is the conversion, the effectivity of conversion of microorganisms to carbon dioxide, water, and other inorganic products. Well, this is quite reasonably easy, the respirometry, well, to understand at least, because you assimilate carbon by the amount of 14 carbon 14 isotopes, because there is a precise amount of carbon 14 into the general carbon, so you may find out that you, in the end, you end up with an incubation, a graph which gives you an incubation and the amount of carbon dioxide which is in. I don't go into the details, but you easily understand we have this kind of fermentation, some kind of pressure and so on, and you measure by analyzing the gas by the infrared cell and the amount of oxygen by a paramagnetic cell. You end up with information about the evolution of carbon dioxide with the incubation time. This kind of S curve, which you see top left, you can see that there is an initial activation of the gas, so-called lag phase. Then you have this evolution, and in the end, you have the kind of plateau. Plateau means that you have already decomposed most of it, and therefore assimilated into soil. But some remains to be done, but it's done at a quite constant rate. Okay, and apart from the measurement you can perform, which you can see are a number, you can make a number of measurements. I've shown briefly the respirometry and the respirometry and that other possibility to measure the realization by simple calculation, always on by calculating the carbon dioxide emission. There are a number of other possibilities. I don't go in much detail about that, but you can do studies on the enzymes. Instead of studying the carbon dioxide, you can study the enzymes, what happens with enzymes. And because instead to study the bacteria, you study the enzymes which are produced by the bacteria and which can be developed to close the cycle to produce other biodegradable materials with extraction. We can use the enzymes, and the problem is that enzymes are very active, and therefore their amounts can change from time to time. You can do, as you can see in this table, which is from a study which came out in '96, but it's well, the question, maybe the equipment have changed, that be evolved, but the question is always the same. There are some measurements which can be easy but slow. For example, you can simply expose into the field, then take some sample from the soil from time to time. The advantage is that natural is you have natural conditions to expose to, or otherwise you can do that in the lab. But then the natural conditions are reproduced, and you might be quite dubious on what you get out, because you might be able to reproduce it in natural soil. The advantage is that you can test the single product, which is not, for example, take a plastic bag, and you can see I decompose that very plastic bag, and I can see what really happens in terms of assimilation, which is not the case in the field. Well, yes, you can. I can grind that plastic bag, but of course, in the soil, this is mixed up with everything else. It's out of my control, really. Okay. Then you can have one technique which is very interesting, and I spend some few more words on that. I understand that a course on techniques would be fascinating, but it's out of that general course, out of the objective of the general course. What I can say is that the radio-labeled polymers are very precise, with all respect to all other evaluations. Because, well, respirometry is connected to carbon dioxide, but then I have to be sure that all carbon dioxide is produced by my process. So I need to have a control which is completely fine. But then I need to be sure that I am just using that kind of material, and not there is no anything else. This is true for field export, will be even worse. In other cases, I have lab experiments, and again, how much I can reproduce the real condition. Radio-labeled polymers are fascinating because I can label my polymers with some radio components. You may know that there are some isotopes, not only in isotopes from uranium, plutonium, and so on, from the real radioactive elements, where the main isotope, so the isotope more present, like 238 for uranium, is really radioactive. I can have also some lower quantities, which are radioactive, which tend to decompose, and of which I know the half-life. So in the end, I can label my polymers by grafting to the molecules some of these isotopes, which is tricky but can be done. And in the end, by comparing the half-life of known half-life of these isotopes with what happens in the polymer, I can measure the degradation velocity of. Okay, this is what I can do in terms of techniques. There is one thing I didn't talk about because I need to concentrate a little bit more on that, which is BOD. BOD is biological oxygen demand. Biological oxygen demands means the amount of oxygen which I need to oxidize the biological matter which is present into my material, to my matter, my waste. So biological oxygen demand is also one of the indicators of pollution and of the presence of waste which is not inert. Because of course, if it is inert, it is sand. Say, I don't need to oxidize it. So in reality, there is BOD equals 0. It was just sand. In reality, if I have biological material into decomposition, I need some oxygen to accelerate the decomposition. And I will come back to BOD later on, just for more precise indication on what can be the values which are interesting for composting and for assimilation and for making a good quality compost. You need to clarify. I give you also some references because coming back to Greta's issues of the fact that fragments, plastic fragments, are present in sea at sea, I need to make some further considerations. You can see here in that table what we see to the left are some names of microorganisms. This is a recent study in 2018, which came out in 2018, which wanted to review which kind of microorganisms were able to decompose which plastics found where. Why this was done not in the lab? This is very interesting because it was done in the lab, but from plastics not bought down the market. Of course, I can buy polycaprolactam over Amazon, but then, and I may find out that some bacteria are able to decompose it at some speed, which is good, commendable, but which is good, but with some limitations. That I am not sure of the real velocity that will be the true one for microorganisms in a specific environment, because pH changes, salinity changes. Because, for example, I may simulate the salinity of a sea. Salinity changes from sea to sea. There are, in terms of amounts of salt, and in terms also of type of salt, because there is sodium chloride, but there is potassium chloride and other complex salts, which contributes to the whole of salinity and so on. Then there is the hardness of water, so the amount of carbonates and so on, which also contribute to that. After that, it is important to dispose of some local information about local in terms of referring to plastics collected in a definite place. So the places are indicated. And we found out interesting things. For example, polycaprolactam. Polycaprolactam is very promising because, well, it's expensive, really expensive. I can give you also some figures, but it's well, to buy a little bit of it, a little bag of it, you may need 20 or 30 euros. But anyway, it's expensive, but it's also promising because it's produced from petrol, but it is biodegradable. Produced from petrol, biodegradable. Then we have, but we don't have only plastics which are known to be biodegradable, like PCL, or which have a kind of interaction with, they are not biodegradable, but they have an interaction with water, at least, like polyvinyl alcohol, PVA. We have also some other plastics which are not biodegradable. Also, like polyethylene. Polyethylene is based on a polymer which has no oxygen, hydrocarbon. So it's not supposed to have any interaction with seawater. Having said that, some of these bacteria were able to produce a better or lower interaction with their plastics. I would like in the next few lectures, since this will be the last one for the first part of the course, to go into more details about these studies, because in some cases some results were really interesting. Um, these studies don't say that everything was wonderful. They say that there is a little bit of biodegradation, so degradation from bacteria, even in plastics which were not biodegradable. In the second part of the slide, you can see again some bacteria which were connected with some microbes. This goes beyond what you see on TV, etc. Because if you throw it, well, please don't throw away bottles. But anyway, if you have a plastic bottle which is at sea, it is not completely true that it's not biodegradable. That's what we tend to think, because information on these things is quite, in some cases, somehow rough and imprecise. But I'm not saying that we need to throw at sea PET bottles, but I am saying that there is no interaction between any bacteria with this kind of plastic. There are some bacteria which have some kind of interaction with these plastics, and these things are studied. In the UK, they were very active because the UK, you know, it's a bit in between because they don't want to follow the American way because they are not in the position to do that. The country is smaller. The amount of plastic consumed is quite large. Landfilling is not suitable because there are areas where there is no land to fill, basically, because it's a quite flat land, no desert and so on. So you can imagine that in the UK they don't want to land plastic. On the other side, they are surrounded by seas, which are heavily polluted ones. In a number of investigations, on, especially on plastic bottles, on which kind of bacteria are able to feed on anything for plastic bottle, which might not be PET itself, might be the additive. They might feed on the additive, but they are able to live on plastic. Because it needs to be clear, if something is at all not biodegradable, any bacteria wouldn't be able to feed on any part of the plastic, on any component. Instead, there is some kind of interaction. My aim would be to go into more details about that because this is innovative and this is, I'm not sure that it's the way to follow, but in some particular cases it might work. I come back to BOD. Remember that, for example, BOD affects water quality. So if we want to come back, for example, if we assume that it's not just a question of seawater, what happens with microplastics is that microplastics also affect the quality of water streams which we ultimately drink from. Therefore, here these are some indication in milligrams per liter, and you can distinguish between two types of BOD. So a first stage, which is the carbonaceous stage, and second phase, which is the nitrogenous stage. So in the end, you need to convert everything to nitrate. A good indicator of when pollution has gone into water is that there are no longer nitrite, but there are nitrate. You may remember that nitrogen has got two numbers of oxidation. The lower one gives rise to nitrite, the higher one, well, the main in reality, these are the two main ones. In reality, nitrogen has got five numbers of oxidation, but apart from that, we need to get to nitrate because the number of oxidation cannot grow anymore. So all the oxygen that has been taken, and the molecule cannot evolve anymore. And that means in practice that the molecule is stable. Nitrate molecules are stable. And I can go into more details if you wish, if you ask me and so on. But the question is that nitrates are, and if you look at mineral water, you have nitrate are allowed to be present. Instead, nitrate are not. So in practical terms, we calculate biological oxygen demand grams per liter, and we can measure it. It's a reasonably easy way of measuring it. We introduce large amounts of oxygen to oxidize, and we see how much of it is really consumed. Of course, there is not only biological oxygen demand, but there is also a chemical oxygen demand, and the ratio between the two means that you may have waste which is more or less biodegradable. The highest is the BOD over COD ratio, the more biodegradable is your waste. So chemical oxygen demand means that you have also other chemicals biodegradable and which need to be oxidized anyway. So you don't have chemicals which are basically synthetic chemicals, but in any case they cannot have any kind of biological interaction. If the BOD over COD ratio is too low, the material you have is not biodegradable. If you have mainly hydrocarbons and so on, it's considered not to be. And in water treatment, you don't treat water with bacteria, which are very common bacteria to the common ways of treating water, or you may have active carbons and so on. You therefore need to know this kind of ratio to understand whether you can do something wrong in terms of biological action. I am also saying that because of what I was saying before is that this ratio needs to be modified further if we discover other bacteria which are able to water even with low BOD-COD ratio. Okay, of course, becomes tricky in terms of drinkable water because there are requirements which are stricter and so on. But for general water of industrial use, it might also be the case. Even water which is heavily polluted might be subjected to biological. So it's likely that the limit will go down the possible biological. Bioplastics. Let's come back to bioplastics on the last few slides. So we summarize what we know about bioplastics. This is important because something we know them already. We have to define first of all what we know about bioplastics. Bioplastics term is confusing. The term is bound to disappear, I suppose. I suppose in a few years we will be more precise about bioplastics, about what we mean now for bioplastic, because there are different categories and there is a kind of mix-up. We may have some agro-based polymers blended with biodegradable synthetic polymers. What does it mean? For example, I may have a PLA mixed with PCl. PCl is a biodegradable synthetic polymer. PLA, in principle, at least, it's an agro-based polymer. In principle, because it's based on cornstarch. Although cornstarch is decomposed into sucrose and then repolymerized as PLA, polylactic acid. Then we have polymers which are obtained from microbes, and these are the polyhydroxyalkanoate, PHA, which is again a patent which came back from the 30s, which basically came back from the 30s, but again, it's connected with work on Pasteur on pasteurization and therefore on the possibility of develop sugars from organic matter, to extract sugar and to by the action of bacteria, like bacteria working on yogurt. It's not very different from that. And you have this kind of fermentation, you produce polymers from which you develop plastics. Then you can have monomers and like PLA. PLA belongs more to C than to A. I was mentioning it into A because in principle, if you make really it from cornstarch, then you can consider it as belonging to A. In reality, the industrial process makes PLA more closer to C. A is when you take really starch and you can extract PLA, or you can make it simply using the starch, a thermoplastic starch. So you can also mix up starch with glycerol, with acetic acid, and make a biopolymer. And probably also blend it with some other polymers like PCl. So then you can have some other possibilities which are involved in the D category. D category, there are some other materials which are obtained from petrol, which are of petrochemical origin, like polyesteramide and PVAT and so on, which are of petrochemical origin, but they are mineral purpose, they are biodegradable. You may see that we are getting more and more confused when using the word bioplastics, because you can, if I want to simplify that, I would say we have thermoplastic starch, so plastics obtained probably from waste, really from waste. Starch you can find out as a common waste from a number of products based on flour, or even there is also the possibility, which is not mentioned here, but the possibility to have biodegradable polymers made on whey, so milk whey, so on proteins. These are again biodegradable. Then you can have the polymers obtained from the microbes, and some of the bacterial polymers, some of the polymers are mentioned down here in the slide, at the end of this slide. But there are many more which are investigated. Then you can have some materials of petrochemical origin. And of course, there is the real way to produce PLA. PLA is undergoing a lot of development, lots of development. They are trying to make the chain longer, to make the material stronger. Therefore, possibly not compostable. It would be biodegradable, but not compostable. I would like to say, to be frank, that another term which creates lots of confusion is again compostable, because compostability means that it can be introduced into compost at definite conditions. But in reality, as I was saying also last time, compost, it depends as well on local conditions. Of course, the producers, compost producers, would like to sell their compost over the world, but in reality, the reliability of compost, the performance of compost depends on the place where you are, pH of your soil, on the amount of minerals, or which kind of minerals are more frequent, if there is more calcium carbonate or hydroxyapatite. So you see that this is not easy, but it's important that we try to understand what's happening more than giving simple and false answers to these questions. So polyhydroxyalkanoate, basically, they are produced with low limiting nutrients. So if you have phosphorus, lots of phosphorus and lots of sulfur, nitrogen, and oxygen, you may have problems. But if you have excess carbon, you may be able to produce that. What I'm saying, this is the kind of diet that bacteria need to be subjected in order to produce polyhydroxyalkanoate. Then there are two different types: short chain and medium chain. I'm sure they will develop also long chains one, because longer chains means that the material is usually stronger and so on. The interesting thing is the last one, that around 150 bacteria, and this study was from 2015, so probably now they are even more, they have produced some form of pH. Please remember another difference, that with plastics, with non-biodegradable plastics, we need to stick to a few plastics. Practice called the plastic collection system has been limited to a few types of plastic: polyethylene, polypropylene, PVC, polystyrene, basically. Not much more than that. And PET, which is always a derivative of polyethylene, it's a polyester derivative. In the end, we need to concentrate on a few plastics. Here, it is very interesting, that one, because everyone could produce its own PHA with bacterial strain. This is interesting. This is interesting because since they are all biodegradable, of course, you need to investigate the velocity at which they are biodegradable. But provided they are all biodegradable, in the end, you may be quite sure when recycling them. You can recycle them also by that cycle I've shown you. You can put them in the soil, then extract some bacterial strain from the soil, and then reproduce the plastic, the bacterial. It should be something that should be interesting. This is how it happens, to show you in practice what happens. Of course, you need to provide the right diet. saying, a bit showy way, but it's really a diet which involves the right amounts of hydrogen, sulfur, and so on. And then you have a time of incubation, and what happens in reality is that these bacteria create cysts in which there are granules. It is also interesting that these plastics start like granules, which is very good in some terms because we may incorporate those granules into the polymers, uh, plastics, I would say, because to really polymer granules, polymer pellets, for example, for um, injection molding and so on. This is a bit science fiction at the moment, but that's the perspective that we are able to include this kind of bacteria into PHP, which is already sold as granules, although just by a few types of bacteria. This is a study which is interesting, was performed in Romania, about different places in the country where the bacteria fed on what they were able to find in that soil, were developing different ways. Even the dimension of the cysts, the system and the granules was different. So it's important to remember that bacterial polymers can be related to the soil in which they are. So it becomes, rather than having a plastics for everyone, rather having a plastic focused on the place where this is produced. I'm not sure how much this is feasible. I'm not sure how much this is going to evolve. Bacterial polymers are definitely expected, which will close the cycle in another way with respect to the grade-to-grade cycle, cycle of bioplastics. Okay, next time we are going to concentrate again on the sense of composting. I would like to explain a little bit better the question of vermicomposting and of how this can be suitable for always in terms of sustainability. Okay, as always, if you have questions, please feel free to send me an email or contact me in any case, and see you on Wednesday at 2. Okay, these slides will be available later today on my webpage on the website, on the university website. I hope you were able to find it. Now all are there are the folder sustainability, and of course I put the slides time over. Okay, so see you on